I'm presenting today the PhD results of my student, Qinshuo Shen. I'm from the University of Twente in the Netherlands, the eastern part of Netherlands. And I would like to present an ongoing project that we have within a kind of research network.
All right, I'll try.
So we do have a research network at the university called ASPARI. The main focus of ASPARI is actually innovation within asphalt construction sector, with main focus on construction processes. So what we try to do is actually to monitor the construction process of asphalt in general, and then try to see how we can intervene in order to improve the processes. That's the main focus of ASPARI. The project that I'm presenting today is one of the projects that we do under this research network, ASPARI. And the main idea is that we are seeing the transition from hot mix asphalt to warm mix asphalt, and for a good reason. You know that asphalt accounts for quite a little bit of CO2 emission, and part of that, or great part of that, is because of all the heating process that would go on for the hot mix asphalt, and then the transition to warm mix asphalt, which basically allow us to compact asphalt at a much lower temperature, would allow us to consume a lot less energy and also bring down the CO2 emission. So there is this national push from the government to move towards warm mix asphalt. But then the main problem with this transition is, although the material more or less remains the same, the way that you're handling this material is inherently different because of all the additive that you add to the asphalt. So because of that, the way that you are approaching the construction process need to be completely different. And you need to take into account all the variability that comes to the process because of this change of material. And that basically means the approach that you had with the tactical planning of hot mix asphalt cannot be simply retrofitted to warm mix asphalt. You need to have a different approach. But then if you look at the industry, the main problem there is that they do not have sufficient tools to be able to relate the impact of changes that they would make to the tactical planning on the actual quality of the asphalt. And asphalt is, again, a very tricky material because you have only one go with the construction process. And if you don't get it right, the consequence of having it fixed would be normally quite high. It's commonly very costly. The repair would be very costly. So it's very important, and the damages a lot of time could be irreversible. So it's very important that you get the planning and the strategy right. And there are no, let's say, technical supports for the planners and the tactical teams to be able to understand and evaluate their different strategies. And normally they rely on their own past experiences. So over the past few years, focusing on hot mix asphalt specifically, we try to develop simulation tools that would allow the tactical team to play around with their compaction strategies. And when I talk about compaction strategies, it's mainly about the temperature window that the operators have in order to compact the asphalt. And that temperature window is actually quite small because you can't compact the asphalt when it's too hot. You can't compact it when it's too cold. So getting that compaction window right and then making sure and steering the entire process so that all the compaction is done within that time frame is quite tricky. But then the main problem with all these simulation models that we've developed, and these are high fidelity simulation with very precise visualization. But the main problem is we assume if certain number of compaction passes are done at certain temperature, the asphalt quality is good. And that's a wrong assumption. Because a lot of time, especially with warm mix asphalt, because you have a lot of additive, the way the material would respond to the changes in your strategy would be quite different. So inherently, you need to incorporate some sense of physics into your model so that once you're simulating, let's say, different strategies of compaction, the asphalt material would react also in a sensible way to how these strategies are being manipulated. So if you look at different approaches that we have for modeling the behavior of material in general, the most important one, or the most sophisticated, well-studied approach, is using numerical models, or what we call physics-based model, that is inherently based on particle simulation. So you try to simulate the contact principles or mechanism between two particles, and then you can calibrate it for any type of material, and then you will be able to mimic the behavior, the physical behavior of different material, including asphalt. Of course, this is a very well-studied subject. A lot of people develop physics-based model, but then the problem is when you want to bring that model into a tactical planning tool where you want to do simulation of 1 kilometer of asphalt road, it's not going to work. These are very, very slow tools. Each run of this simulation, depending, of course, on the machine that you're using, could take anywhere between a few days to a few months. And that's for a very small sample. And now we are talking about a very long stretch of road, and you would like to use that kind of numerical model. It simply would not work. And that's why most of this physics-based model would remain, or their limitation is, their application is limited to, let's say, laboratory testing, some initial testing, and never actually into tactical planning. So that was the problem that we face and we try to address. And our approach is surrogate modeling. So surrogate modeling essentially is whenever you're dealing with very computational intensive physics-based model, you try to develop an approximated model of that complex simulation using some random data generated from that simulation model, and then applying machine learning on that randomly generated data set. And if you're able to approximate that model with your machine learning method, then you are basically substituting that complex computational intensive model with a model that is far more efficient in terms of computation time and computational effort required for that. So that has been the main objective of this research. Are we able to develop a surrogate model for warm mix asphalt? And well, we knew that the answer is yes, but the main question is, how can we do that? What are the steps that we need to take in order to be able to develop a surrogate model for warm mix asphalt? So the approach is rather simple. So Shen had to spend a lot of time looking into different contact models that are available, pick the one that could be best calibrated for warm mix asphalt, perform proper testing of that physics-based model to make sure it's accurate enough, and then look into or go through this design of experiment setup where he tries to build a database that would cover the entire range of possibilities of that physics-based model with a few random shots, and then try to develop a machine learning on that data set and assess and evaluate to what extent that surrogate model could be accurate or as accurate as the physical model. And then you can use that surrogate model for whatever task that is you want to do with using that physics-based model in a more integrated platforms, such as the tactical planning tool that you would like to develop. So this is the physics-based model that Shen developed. And the idea is he tried to mimic gyratory test, because that's the test that we are going to use in order to calibrate our model and also assess to what extent the material is actually representative of the actual physical mix that you want to use in the site. So he developed this gyratory compaction test in a physical environment, or well, in a numerical model, and then he applied the contact principles, and the entire asphalt behavior could be actually regulated by 3 main parameters. One is basically the elastic force between 2 particles, the damping between different particles, and also the aggregate size of different aggregate that you will have. So the composition of the aggregate mix. So these 3 elements together would actually give you, and also the additive that you would add. So these 4 different elements would allow you to be able to model and mimic any kind of mix that you would like to use in your actual project. And then, so he did a design of experiment. He looked into different parameters and the possible ranges of values that you could assign to the different variables. He applied a kind of established design of experiment method to generate a lot of random data set. But random, it should be random, but at the same time, it should have a kind of fair distribution and representation of all possibilities across the entire continuum of solutions that could be potentially covered by this physics-based model. And then he actually created 500 instances of different types of mixes. And this practice by itself took him, I think, if I'm not wrong, three to 4 months just to be able to build this data set. And that would tell you already how difficult it is to use this kind of physics-based model. And then again, don't forget, he wanted the scale of his model was only this very small cylinder, not kilometers of road. And then each run would take 1 week or 2 weeks, if I'm not mistaken. So with that, he tried to apply different type of machine learning on the data set that he built. And then, of course, he did some analysis of the models to see which one is more accurate. And again, based on all the previous experiences that we had with similar type of research, as expected, random forest was identified as the best fit for the data that we have. And then we got quite acceptable performances for the multi-output random forest. And then what we did for the validation, now instead of using the actual physics-based model, we tried to use the surrogate model that we got, and then we did some laboratory tests. So we went to the laboratory, we pick up a warm mix asphalt, we did the gyratory test, and then we got the densification curve out of the test, and then we tried to see if we can use a meta model to calibrate the model for that specific mix. And the most important parameter or factor for the success of the model, of course, everything about the goodness of the fit of the curve is definitely a parameter. We got pretty good numbers. As you will see at the higher temperature, another main advantage of this surrogate modeling approach is that this physics-based model, they are normally developed for only one temperature. So they assume that the asphalt temperature would remain at 100 degrees. And this is not the case, because when the temperature decreases, the physics behavior of the asphalt would also change. So if you really want to model the physics properly, the physics model needs to be temperature sensitive. And you can't do that with the existing physics-based model, because if you want to incorporate also changes or variation with the temperature, that would add a lot to the complexity of the model. But with meta model, that's actually quite simple, because every run of the model would take a fraction of a second, right? So the whole calibration of the model for a whole mix, considering temperature variation, would take only a minute or two, right? Considering the temperature variation. So that opens a lot of doors for us to be able to use this kind of physics consideration into the model. So what we saw at the higher temperature, the performance of the model is very good. But as you can see, when the temperature goes down, the accuracy of the model goes down. So I actually had this discussion with Shen a week before I come here. And we look into the causes of that. He had his own justification, but then when we look at it, the problem was his design of experiment. So at the lower temperature, the data that he had in his data set was actually not sufficient, or it was undersampled compared to the other temperature. So he had to beef off his data set so that he has more representation at the lower temperature. So I told him, can you do that before the conference? And then he said, no, it's going to take another 2 months. So that's why I could not actually have the updated value of these curves, but we are quite confident that more or less we will get the same type of accuracy for all temperatures once the data set is more level and more uniform. So to conclude, the key finding was that we are able definitely to develop meta models. to surrogate or to substitute complex physics-based model of the asphalt. And the next step for us is to actually scale this up. So now we try to use this meta model only to replicate the gyratory test. But then what would happen if we go to the much larger scale of a stretch of road? In terms of computation time, how much would that take? And of course, we need to make also some additional simplifications. I'm not going to go into detail, but maybe you need a surrogate model of the surrogate model to be able to scale it up for the entire stretch of road. So that's the future steps of his research, and Shen is going to be busy with that over the next year. Yeah. So that's about the presentation.